This is House Planning Help episode 325. Hello, I'm Ben Adam Smith, and this is the podcast for you if you're interested in self-build or retrofit. I'm exploring what houses we should be building in the 21st century and trying to break down the major roadblocks that may get in our way. Coming up, my guest is architect and passive house designer Mark Siddall. His practice, LEAP, Lovingly Engineered Architectural Process, that's the acronym, operating in the northeast of England. And today we're looking at air movement around insulation. Could be across insulation, could be getting through insulation. It's all bad news, I'm afraid. But first, it's a bit dramatic for this podcast, isn't it? Thank you to Stephen Miller in Oxfordshire. There is a reason I've played that. And he spotted this in the Journal of the Institute of Engineering Technology. They have this column called Dear Evil Engineer, which is a podcast and also a YouTube channel. And villains write in for advice on their diabolical plans.
I have 2 fearsome pet leopards, and I was already considering buying more. How many would I need if I wanted to heat my pleasant 2-bed semi-detached entirely with leopards? Yours, a conscientious villain.
Now, you're going to have to check out the full video for all the maths behind it. It goes into quite some detail, but very excited that they mention a passive house and say that that would be the best way of going about this riddle, and then a normal building regs house. And do you want the answer for a passive house? I think so.
For an average UK house with floor space of 96 square metres, that gives us 1,440 kilowatt hours per year in heating. A single leopard can generate 392 kilowatt hours per year in heating, so 3.67 leopards, alright, 4 leopards would provide all your heating needs in the most efficient house.
I'm fairly confident that you wouldn't have put that on your choices for heating sources. A nice passive leopard. Thank you, Steve, once again for alerting me to that one. Mark Siddall is a passive house specialist operating in County Durham and Newcastle. He's also a technical advisor to the Passive House Trust and the AECB. And it's in that capacity that he's written a paper on thermal bypass risks for the Passive House Trust. And we're going to find out how that might impact us on a self-build or retrofit. We start though, you might have heard of the performance gap before. So I wanted to ask him, what exactly does this mean?
There's not necessarily one performance gap. There are a number of different performance gaps that could be considered and explored. When we're talking about passive house buildings, the conversation has a tendency to focus on energy performance rather than air quality or other factors. And when we're dealing with energy, it's often the thermal performance of the building fabric. So that's the key area that we'd be focusing on in terms of thinking about performance gaps in this particular conversation, shall we say.
Often we get told to insulate. It's a very singular message. And I know that that's one of the reasons that I like passive houses, because I know under the hood there's all sorts of work going on, and that if you follow the formula, then that reduces things a lot. So if you're in a typical house and you're using insulation, big question here, will it work?
Maybe.
Diplomatic, like it.
Yeah, well, there's a number of different variables that will influence whether it works or not. And for the purposes of today's conversation, we'll just put things like thermal bridges, so cold spots, we'll put those to one side, and we'll just talk about how the insulation properties actually work and how that can impact upon performance. And in that particular context, it comes down to whether the material itself is specified sympathetically for the construction method that's been used, and also whether then it's been installed properly. So there's 2 variables there that we really think, well, 3, I suppose. There's the material itself, there's a specification, and then the implementation.
All 3 of those right, and you're winning.
That's it. Yep. If we get all 3 aligned with one another, which we do in a passive house design, as the evidence would show, then that's when everything works properly. It's when we deviate from that things can go wrong. And we see quite a lot of case studies that show when it goes wrong. And there's the Leeds Beckett University have got a good database where they did a co-heating test. And I don't need to get into the intricacies of how it works necessarily, but basically my metaphor is it's a bit like when you go and get an MOT done and you put the car up on the chocks and you can test all the different variables. Well, this is trying to do the same thing for a house or for a building. And the evidence shows that even well-meaning projects that have tried to close performance gaps often fail when they're approached with a building regulations frame of mind, shall we say. Whereas when you compare that to the passive house projects, they actually close the performance gaps and perform as predicted.
So maybe we do need to go into this a little bit. What is different about what the passive house methodology is doing?
Well, the way that it's delivering a better standard of building fabric is it's got better quality assurance processes and mechanisms deeply rooted in the standard and within the brains of the people delivering these projects. So therefore, we're avoiding risks that might otherwise arise. So when we're thinking about how insulation is specified and used, we're using the right kinds of insulation that work with the particular method of construction that we're talking about. To be a little bit less abstract, if we were taking cavity wall insulation as an example, you could go to any building site that happens to be around you, and you'll see probably that it's cavity wall insulation, that it's a foam insulation that's being used. And the question would, a passive house designer will ask is that insulation really sympathetic with the method of construction? And the answer to that would be no, because you've got block work, but you've also got mortar joints, and mortar is obviously squidgy when it's been installed, and that creates a mortar snot, which projects into the cavity and then stops the insulation abutting the block work along its smoothest face. And that little air gap that we end up with is enough to completely undermine the thermal performance of the insulation. Whereas for a passive house side of things, we're looking at that and we're saying, okay, there may be mortar snots, we want to clean them off. We know it may not happen with 100% confidence all the time. Something like a mineral wool insulation is a lot more flexible and capable of dealing with subtle undulations in surfaces, and therefore that's a much more appropriate insulation to be using in a cavity wall scenario. And we can use mineral wool insulation to the full depth of the cavity, which also helps to reduce the risk of air movement, because it's air movement within and around and through your insulation which has a really significant impact upon its performance.
So that's really interesting. You've mentioned all sorts of things going on here. Let's stick with this masonry example for a second. So when you're doing this well, can you take us through almost some of the layers? Because you're trying to do different things, aren't you? You've got the wind on the outside. You've got the rain on the outside. You want to be warm on the inside. You've got to have this airtight barrier if we're talking passive house as well. So how do we make all of this work then if we don't want the air to just wick it away to the outside?
There's several different factors to go through there. You've alluded to them quite broadly, should we say. If we start with the rationale for an air barrier in the first place, building regulations only really gives us a numerical target for airtightness when we're dealing with heat loss. So Part L of the building regulations deals with heat loss, and it prescribes an airtightness standard of 8. Part C of the building regulations, which talks about moisture, only really refers to that things should be fairly airtight. It doesn't really give you a numerical target, and there's a problem with that. What we know from the passive house standard, and the reason it's got its targets set the way that they are, and also other research that's been conducted in Canada, they both confirm the same thing, that we need to be achieving an airtightness in the order of 0.5 or 0.6 air changes per hour at 50 pascals, or a permeability of around about 0.5. And the reason we want to achieve that is so that we don't get moisture damage to timber structures, so within roof spaces or in a timber frame scenario within walls, for instance. Now, that sets the standard for why you want good airtightness. But that in its own right won't necessarily guarantee that your insulation will work properly. What we also want to be able to do is to make sure that the wind can't blow through the insulation, because if it can get through the outer layer of the insulation because of gaps or cracks or air gaps between or around and behind your insulation, then that air movement will wick away the heat and mitigate the performance of your insulation. So we need to get some sort of wind tightness on there. Now, we can't actually test that on site, but it's a really useful thing to understand the quality of workmanship that would be expected. And what we find when we start to do the more technical analysis is that the standard wind tightness that we require is, broadly speaking, something similar to what we'd expect on our airtight layer as well. Certainly from a visual inspection point of view, that's the rule of thumb. And then we've also got this insulation sandwiched between an air barrier and a wind barrier. We've really got to make sure that this insulation is properly encapsulated. So that means that you've got no air gaps anywhere in and around that insulation. Because you can imagine if you've got a successful wind barrier and a successful air barrier, that insulation in theory could be suspended perfectly in the middle of a void, a space. And again, there's this risk of convective loops, which can arise just because of temperature differences between the warm side and the cold side of a wall, that could mean that that air movement would mitigate the performance of that insulation, or at least undermine it significantly. So we need to avoid that closed loop thermal bypass by properly encapsulating the insulation between a notional air barrier and a wind barrier.
So all sorts of technical terms there, but it's interesting to see how powerful that air movement is. And we talked about designing it out and then the workmanship on site. So yeah, let's just stick with masonry. On the technical design side, you will have had cavity wall construction projects going through your architecture practice. What would those layers look like if you start on the cold side, the outside, and go through? What layers have we got? Can you just talk us through that quickly, and then I've got another follow-on question.
Sure. Okay, so you'd have your brickwork or your stonework on the outside face. You'd then have often a 300mm wide fully filled cavity, mineral wool insulation that's built up in often 2 or 3 different layers. And then you would have your blockwork on the inner side, on the warmer side, and on the surface face of that, then you've got your plaster. And the plaster is acting as the air barrier, and the masonry on the outside is acting as the wind barrier. Because we've fully filled the cavity, we have encapsulated the insulation, and we've got no air gaps around that.
So let's chat about moisture now. So if I understand this correctly, and I could easily be wrong, but the cavity part of the invention 100 years ago, or however long it was that was stopping some of the moisture coming in. So are we expecting moisture to enter that insulation that we've got? And because I had a chat with Bill Butcher a while ago, and I remember him saying something about the weaving of this insulation helps to keep the moisture out. Would that be a fair comment?
Yeah. Okay, so we've got moisture from 2 different sides. We've got moisture from the inside and from the outside. Now, the most dominant moisture problem is the rainwater, the moisture on the outside. When it was first invented, shall we say, when it was introduced in the 1920s or so, the idea was that we were able to then use the air gap as a capillary break. So therefore, the moisture from the rain wouldn't be drawn through the wall. And any moisture that got through the brickwork would then drain down on the inside face of the cavity on the weathering side. Then we could direct that out at the bottom through something called a weep hole. Now, there are certain critical dimensions to the width of a cavity. If you've got a very narrow cavity and you fill it full of insulation, then you've got quite a high risk that the rainwater that could be running down on the inside face could then bridge through to the inside. But the wider that cavity gets, the less risk that you have of that rainwater tracking across. So when we're dealing with cavity widths that are in the order of what's supported by a passive house design, then that driven rainwater risk is pretty well mitigated as long as we've got the quality of the workmanship right, so there are no mortar snots sitting on the beds of the insulation. And also when we're thinking about the insulation itself, and this is getting on to Bill Butcher's point, that the weave of the mineral wool is such that if it's built up in different individual layers, a bit like strata, when you've put the insulation in place, all of those layers are running like sheets of paper from the top to the bottom. So that means you've got successive layers of the book, to keep that analogy going, running through the depth of the cavity. And that means that if any water did get through one layer, it can then still be pushed down and back towards the outside. rainwater would have to work very hard to get through all of those different layers, those different lamellas of the mineral wool itself. So that's how we keep the rainwater out. And even if that does mean that there's a little bit of the outer face of the insulation that becomes a little bit redundant because it's got a little bit damp, that's okay. We can accommodate that. We know that the building will still work fine. But because we've fully filled that cavity, we haven't got the risk of this air movement taking place, which would also undermine the thermal performance.
And you often have these Teplo ties and things going across, so none of these things are affecting the thermal performance.
Well, the Teplo ties, they're dealing with what's known as a repeating thermal bridge. So we're using a Teplo tie instead of stainless steel tie. A stainless steel tie has got a much larger physical dimension and a much higher conductivity. And again, that would undermine the thermal performance if we use them at large. So therefore, we use Teplo ties instead because they're thermally broken.
And joining the inner leaf to the outer leaf.
Correct, yes. Yeah. To help provide structural stability against wind loads and the likes.
So why then have major developers not got around some of the science that we've been talking about?
There's commercial interests at play. Just to point directly to Grenfell, we can see that there are different manufacturers that have helped to try and steer things to suit their own ends rather than necessarily acting for the greater good. And within that, though, there's a slightly more subtle duplicity that's going on, whereby an architect, for argument's sake, most architects out in the regular world, shall we say, away from the passive house context, they'll phone up a manufacturer and ask them to do a U-value calculation for them that will let them understand the performance of that particular piece of building fabric. Now, what the manufacturer never does is actually say, and what quality of workmanship are you specifying? Because if they did, that would inherently mean that you'd have a lesser performing wall. What they actually do in their calculations is they assume that the insulation has been installed perfectly. What the industry doesn't recognise is that that means that we then need to have certain construction tolerances on the building site to reflect that. So therefore, when you put your theoretical foam insulation in a wall and it's installed perfectly, then you can get the U value that was predicted in the calculation. But when it's less than perfect, which is what you see on every single building site, because no one ever talked about the quality of workmanship that's required, or the specification of the materials to make sure that they're working sympathetically with one another, then you've got this scenario whereby things won't perform as we intended, because of these air gaps that will then start to crop up.
If we're the client coming in here and we want our passive house built, I would come to you and I'd be fairly confident, yeah, you know what you're talking about. You're going to do all your side of things in the designs. But what about on site? And I've seen this on a couple of passive house builds where, let's mention my friend Mike Coe, who he was out on his masonry construction after the builders had gone home, pulling out the insulation and putting it back in after he'd got all the mortar snots off and so forth. So is there anything we can do short of what he's doing to keep an eye on that workmanship for our passive house? Or is it time to look at other ways of building that are not masonry?
Yeah, well, I think there is plenty of reasons to choose something other than masonry. It was a starting point in our conversation. Because it's widely used, there are other technologies that are preferential. Timber frame being the obvious one, because it's easily adoptable, it's widely used, familiar in different ways, and we can address performance gaps very well using that mode of construction as well.
Is there an obvious wall build-up of timber frame that we like to use for passive house?
Yes, I think there is a generalised approach that seems to be working fairly well. And if we go from the inside to the outside, we'd have plasterboard, we'd have a service void that may or may not be insulated, ideally not insulated because of the time and labour and material costs associated with it. But sometimes in the northeast, for instance, often we might have to insulate it just to try and get the U values that we're looking for. You then have an airtight layer. You'd then have an engineered I-beam. And between the engineered I-beam, we'd then fill it with a cellulose insulation, for example. Then you might have some wood fibre insulation on the outside and a wind barrier membrane on the outside face of that, and I'll come back to that in a moment. Then we have a drain cavity, which works as that capillary break, and then we'd have a rain screen on the outside face. Now, some of the more recent information that I've been reading, geeking out on research from places like Sweden and in Canada, they've observed that putting the wind barrier membrane just on the warm side of that wood fibre insulation that I mentioned, which might be just 20 millimetres thick, by moving the wind barrier onto that warm side, significantly reduces the risk of condensation because of radiant cooling, so night sky cooling that can happen. So there are still refinements that we can do in the passive house timber construction that would make it even more resilient than it already is. And I'm not suggesting that in the UK climate putting the wind barrier on the outside is going to cause any significant risks, but there's just a little tweak that we could do to make it even better.
So the performance gap in timber frame then, where does it occur? What is a typical place that we might find the air moving?
The research that's been done by the Building Research Establishment looked at industry standard timber frame. The difference between what we've just described before for a passive house versus regular industry timber frame is that you wouldn't have the wood fibre board, you would not be using engineered I-beams, you'd be using a standard timber stud that might be about 140mm deep or so, and you're less likely to have that service void that we discussed there as well. So you've probably got services penetrations through your air barrier that will allow moisture from inside the house to get into your timber frame, potentially causing moisture damage within the structure. So there's the moisture performance gap in this particular context when we're thinking about that and why we want our good standards of air tightness. In terms of thermally, the research has shown that more frequently in the UK, what we find is that timber frame has worked quite well. The U values that are delivered in a timber frame construction are more reliable than they are in standard build cavity wall construction. And the reason for that is if you're using a 140mm stud, often the insulation ends up being 150mm. And therefore the insulation, because it's that little bit bigger than the timber it's going into, it gets a little bit of compression. And it ends up being snugly sandwiched between your air barrier and your wind barrier. And therefore you've got less risk of these convective loops, the warm air rising and cold air falling within that zone between the air barrier and the wind barrier. So timber frame just inherently tends to work a little bit better within regular UK construction. When we move into the passive house context, when we're using blown fibre insulation, that fully fills the gaps between the air barrier and the wind barrier to again mitigate this risk of closed loop thermal bypass so that these walls perform as predicted.
Looking across other build systems, particularly ones with low embodied carbon, is it still air movement that's causing the main problem?
Yes, air movement is kind of a key feature that all construction technologies will have to address, should we say. Basically, the physics remains true, and we've just got to understand how we can adapt the construction technologies to address those key issues of the building physics. Now, whether that's preventing moisture getting into the construction to help preserve it, so they're good standards of air tightness. How do we do that? For a straw bale, for instance, well, a lime plaster on the inside or a clay plaster that can provide the airtight layer. How we think about interfaces and other things, other subtleties and complexities, which are another conversation. But it is a case of limiting that airflow and that air movement through and across and within the wall construction so that the building can perform as predicted.
One thing we haven't talked about is roofs, so I don't know whether that's opening up another whole conversation that may confuse us, but how does this affect the roof space?
The broad principles that we've discussed so far all carry through to a roof. What we can then start to talk about is what kind of roof are we talking about? Are we talking about a warm roof construction, in which case it's very similar to the timber frame walls that we've just discussed. We can just crank it through an angle and carry on. We just changed the rain screen that we had. We just changed the tiles or some other suitable roofing material. Where we start to deal with the cold roof, which is perhaps your standard attic roof, where you've got the insulation running across the ceiling level and then you've got the roof space up above. That's quite a risky space to deal with from the moisture perspective, which is one of the key reasons why, again, Passive House looks to have that high standard of air tightness, because that's where we've got that risk of air movement through. So, for example, if we've got a 2-storey house and we have a 1 millimetre wide gap that's 1 metre long, we can have 2 pascals worth of pressure being applied to that ceiling. Now, what's 2 pascals worth of pressure? Well, if you've got your good quality photocopy paper, that normally weighs about 100 grams a metre square. That's basically 1 pascal worth of pressure. So we're talking about 2 layers of photocopy paper pushing upwards rather than downwards, pushing upwards against your ceiling. And over the course of 24 hours, through that 1 millimetre wide, 1 metre long gap, around about 360 grams worth of moisture can be transferred through that. And broadly speaking, from the information that I've seen, around about a third of that could condense into your roof construction. So that's why we want good standards of air tightness. Whatever moisture does get through into the roof space, we've got to be able to then remove. So we need a vapour permeable underlay on our roof construction. We can also ventilate that roof space. There's arguments and reasons why that may or may not always be preferable, or you may not be able to do that. But if you can ventilate that roof space, then you can remove moisture. But the question then becomes, when we start to look at an eaves detail, what's the risk of this wind washing taking place again? You know, when the air's coming into the loft, it's coming at a higher speed, higher velocity, and therefore we need special details around that eaves detail to help protect the insulation at those vulnerable edges from that air movement.
It always seems that it's very complicated. We're talking about houses, which must be one of the simpler things to do, but are we on a path to simplifying things, and what would that route be?
There's a lot of thought, shall we say, there's a lot of things to consider when developing a detail, but that doesn't mean that the detail has to be complicated. To make it buildable, the art of the design is actually simplifying those details so that they are very easy to replicate, you know, from person to person, site to site, project to project. It takes just as long to design a good detail as it does a bad one. I don't think it takes me any longer to design those details, because once you've got in the right frame of mind, certain things come effortlessly. So therefore, you're just designing the detail and addressing these things more automatically. So it's not that there's more time from a design perspective that has to go into it when you've got the experience.
Is there anything else that we haven't mentioned in this conversation that would be appropriate to a homeowner, either buying or going for a self-build journey, some parting advice to try and avoid these issues that we've been discussing?
Yeah, without getting sucked into too many details, it is keep it simple, and it is to remember to make sure that you have an air barrier, that you have a wind barrier, and that you encapsulate the insulation. And as long as you do those, 3-4 things, then you're on the right path. There's all sorts of levels of detail that you can go into to how you deliver that, but those are the basic principles, the key takeaways in this particular context.
So, Mark, for anyone who wants to dig deeper into this paper, can you tell us where it is and what it covers?
The paper is on the Passive House Trust's website, and it's entitled Thermal Bypass Risks. And it's also packed full of solutions and tips and tricks that designers and architects can use to help mitigate thermal bypass within their building projects. It could be picked up by a brave self-builder, shall we say. It's broken down in a section so that at the end of each section there are some takeaways presented in a fairly accessible format. So I think your listenership should benefit from that.
Mark, always a pleasure. I'll chat to you next time.
Wonderful. Well, thanks a lot, Ben. You look after yourself. I'll speak to you again soon.
Get a summary of today's session at houseplanninghelp.com/325. We got links to Mark, to Leap, his architectural practice, and to the Passive House Trust, where you can download his paper, all at houseplanninghelp.com/325. I've got a couple of new reviews that have come into the Apple Store. Hello to Buzz941. The title of this is Fantastic Resource. I'm considering a self-build, and House Planning Help has been a fantastic resource for getting me up to speed across so many different aspects. Keep up the great work. Thank you very much for that one. Also, thank you to Tom in Aberdeenshire, who says, excellent series, really well put together and loads of useful information. If you're thinking, I like this podcast, I wish there was something I could do to help Ben. Well, look, this is your moment, please. Whatever you're listening to us on, whichever app, often they give you the opportunity to review what you're listening to. So please put in a review, try and explain what the podcast's all about for others, and that will help us get to more people. Finally today, my call to action is to check out the Hub, which is our very own boot camp. It's primarily for UK homeowners, self-builders, or people looking to retrofit, but obviously a lot of it just applies wherever you are in the world anyway. We try to use video as our main learning tool, and so we often follow entire projects. Our current one is a retrofit story. It's actually nearing the finishing stages now, and they're on site doing an airtightness test. This is quite an interesting one because it illustrates a key point in a retrofit. So it's taken almost a year, all the structural changes have been made, it's watertight once again, and it's just the small matter of the airtightness. So there are a lot of pressures. It's been a year since they've lived in their home. They want to get back in there. The builder wants to finish the project. But quite often you want to almost pause the project to just fiddle around with that last bit of airtightness. And on this project, there were just all sorts of things. There were labour shortages, there were material shortages, and the sequencing. It all clubbed together to make this very, very difficult. So check that one out as our new one that we've added into the Hub, houseplanninghelp.com/join. All the other things in there are courses, our office hour calls where you can chat to me, our live training sessions, and our members only forum. Get involved at houseplanninghelp.com/join. Thank you so much for listening. The House Planning Help podcast is produced by Regen Media, content that matters.